In this episode 39 of the SOC Level 2 training series, we are going to go through the x86 assembly crash course room, which is inside of the malware analysis module inside of the SOC Level 2 pathway of TryHackMe. And this is the last module in SOC Level 2, and we're going to just kind of keep trucking along with this whole thing. As a part of the outline for this video, we have the intro to the assembly for these. Then we have the opcodes and operands, general instructions, flags, arithmetic and logical instructions, conditionals and branching, stack and functional calls, and a couple of practice exercises. And of course, there will be a conclusion where we review everything that we went through. We'll give you some final thoughts, and you will be dismissed for the day. So that is essentially the overview of the assembly crash course for x86 inside of malware analysis. If you're serious about your CySec training and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the supporter, agent, guardian, and master. Each tier gets their own Discord server and early access to content. The agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@hankhackshackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us jump into the x86 assembly crash course. All right, this is going to be another one of those technical lectures that we're going to go through, so try to bear with me as we go through this thing. I will understand in advance, and I'm just going to disclose in advance that there's going to be a lot of technical jargon and a lot of things that if you are not familiar with malware, if you're not familiar with coding or compiling software or any of those things, these things may go over your head. But again, it's not that big of a deal if you don't understand all of the nuanced details, because the big thing is for you to understand the overall concept behind this, the principles behind assembly. And then once you understand that, you can see how it'll fit into malware analysis. So the assembly language is the lowest level of human readable language. It's also the highest level of language into which a binary can be compiled, or decompiled. So you can take binary and then decompile it into the assembly language. When learning malware reverse engineering, knowing the basics of assembly is essential. This is because when we get a malware sample to analyze, it's mostly a compiled binary, and we can't view the binary's C or C++ code, so any other language code that it might be as well, because it's not going to be available to us. It's going to come to us in binary. So what we can do is we can decompile the code using a disassembler or a decompiler. And the problem with that challenge, or the problem with that step, is that a lot of the information in the code is removed while it's compiled into a binary. So when it's being compiled into binary form, a lot of the written information, key information, is removed. So for example, you don't see the names of variables, you don't see names of functions, and a lot of other key information that would actually help you make sense of it. So the most reliable thing that we can actually rely on would be the assembly code. And that's, again, it's like the next step. So it comes up from binary and it goes into assembly code. And we're going to just learn the basics of assembly so that we can use it in malware analysis as we continue with the malware analysis module and try to figure out what malware does or how it works, etc. We're going to go look at opcodes and operands. We're going to look at general assembly instructions, arithmetic and logical instructions, conditionals and branching instructions. The prerequisites would be the last video prior to this one, which is the overview of x86 architecture and the specific stack flow, which is very, very important. That was like the big takeaway that we got from the x86 architecture room and that video. So if you haven't seen that video, I highly encourage you to go through that video first, because again, there's a lot of technical stuff, there's a lot of foundational stuff that we covered in that video that's going to be crucial in this particular video. So that being said, let's go into opcodes and operands. The code for a program, as it's understood by the CPU and written onto the computer's disk, is in binary format, which means the actual code is basically a sequence of ones and zeros, which looks like this. And they're usually measured in a series of 8 bits, meaning 8 of these ones and zeros. And so the first 4 of those series is going to be translated into something, and then the next 4 will be translated into something else. So for example, this specific one would be, the first 4 would be the letter A, and then the next 4 would be the number 5, which means it would be A5 in hexadecimal code. So if you wanted to convert this from binary to hexadecimal or hex, then you would convert it into A5, and then it's written as 0 times A5 to denote that it's a hex number. The instructions that a computer is going to execute will just be a sequence of random numbers in hex if we look at it with the naked human eye. So among these random numbers are opcodes and operands. And opcodes denote the hex for the actual operation, and operands are the registers or memory locations on which the operations are performed. Opcodes are numbers that correspond to instructions that is going to be performed by the CPU. So numbers that are corresponding to instructions. When we use a disassembler, and we're going to talk about this in a little bit, we disassemble a program, and then it reads the opcodes. It translates them into assembly instructions to make them human readable. For example, in the instruction for moving this 0x5f to the register will end up being to move EAX, and then that's what it's going to look like. So this is literally what the instruction for that specific thing is going to look like. For moving this to the EAX register is going to be move to EAX, and then you're going to remove the 0x5f. When you look at it in a disassembler, this is what you're going to see. This is going to be the line of code. And again, for most people, this is not going to make sense. This last piece might, but when you look at it in a disassembler, this specific instruction for moving that is going to look just like what you see right here. This, I'm assuming, would be the ID, so we can actually see it. So 0440,000 corresponds to the address where the instruction is located. The specific ID, or the line, we can say, inside of the overall file that we're looking at. B8 refers to the opcode of the instruction, which is move EAX. So B8 refers to this piece right here. And then 5F with all the following zeros indicates the other operand, which is this piece right here. So due to endianness, and there's little endian and big endian, so this is different conversation, but let's open it just to see what we'll get in this. Endianness, in this case, we have big endian, little endian, for conflicting ideologies. In computing, endianness is the order in which bytes within a word are transmitted over data communication or addressed by rising addresses in computer memory, counting only byte significance compared to earliness. So it's looking at the significance of the byte compared to the order in which it came in. Endianness is primarily expressed as big endian or little endian, introduced by Danny Cohen into computer science, etc. The adjective endian has its origin in the writings of 18th century, etc. So computers store information in various sizes. You're more than welcome to go ahead and just read the wiki for endianness inside of Wikipedia. But essentially, due to endianness, the operand 0x5f is written as this, which is actually this in this particular case. So remember, it's not the order in which it came in, right? It's due to the significance. And in this particular case, 5f in this series of numbers and characters, 5f is more significant than the other one. In little endian notation is what we're looking at. So there's an opcode for each instruction in the assembly language. There are references for converting opcodes into assembly instructions. Unless we are writing a disassembler, we will not need them, as a disassembler does that work pretty well. It's good to understand what's happening under the hood, and that's why literally we're doing this. So in the above operation, we had 3 parts. The instruction was move. The 2 operands were EAX and the 0x5f. And in this particular instruction, the value 0x5f is being moved into EAX. However, we can also have other kinds of operands in assembly. So type of operands would be immediate. That can also be considered constants. These are fixed values like we have in this particular example above. Then we have registers, which are the EAX in this particular case, which is the location. You can think of it like that. It's a register where the immediate operand is going to be stored in the particular operation that we just saw. It could be something else, but essentially registers in this case would be the location. And as we talked about in the previous video, registers is where a lot of the smaller sized data bits are stored for the overall processing of a computer's operations inside of the CPU. So the registers hold data, just small chunks of data. And then you have memory operands, which are a little bit bigger chunks of data. And these are denoted by square brackets, and they reference memory locations. For example, if we see this, then it will mean that the value in EAX is in the memory location instead of the registry. So again, if it's inside of these square brackets, that means inside of the memory, inside of the registers. So, and not registry, I should say, inside of registers. So I apologize for that. So now that we understand this, we can talk about common assembly instructions. So what are the hex codes that denote the assembly operations are called? And the hex codes that denote what they are called in this particular case are going to be the opcodes, I believe, or it would be operands, I want to say. I think it's opcodes. So let's try opcodes and see if that's the answer. And in which type of operand is denoted by square brackets, and that is the memory operand. So let me make sure my keyboard wakes back up. All right, cool. Now we can move on to general instructions. Instructions in general, so not general instructions, but instructions as an overall concept, they tell the CPU what to do, right? So what operation to perform. They often use operands, and they pull those operands from either registers, memory, or the immediate operands to perform an operation and then store the results in either registers or memory. So the most common instructions that we come across are going to be the general instructions that we can see, and this is what we're going to end up using or finding in reverse engineering malware. General instructions perform simple operations, like for example, moving something from one type of storage to another. The move instruction. So if you actually have ever used the Linux command line, you will end up seeing MOV, and it moves something from one place to another place. So you would move it from the destination to its source, and usually the destination is some kind of a path. So for example, /user /hank/downloads /file.txt. That would be the full destination, and then the source would be /user /james /downloads, something like that. And that's basically what this command itself ends up doing, is that it's just moving something from one place to another, and this falls under a general instruction. It can move a fixed value to a register to another register, and a value in a memory location to a register. So this will kind of help us understand here. In this instruction, in this set right here, we're copying a fixed value to a register. In this particular case, 0x5f is being moved to EAX, right? So we're moving to this place, this thing. And it kind of doesn't make sense, because usually when you do it in the command line, you use without the comma, you would use the source first, and then you use the destination. I think I explained that incorrectly the first time that I tried to explain this, but in operands and general instructions, you can see that you have the destination. So you're going to say move to this place, comma, this thing. And then you can also say on the terminal, you can say move this to this location, and then so this would come right after move, and then there would not be a comma separated. You would just say move source destination without a comma separating them. So in this case, we're saying move to this destination, this piece right here. The value stored in EAX is being moved to EBX, for example. So move to EBX, this specific thing. And then in this case, move to EAX, this specific thing. Now, what we understood earlier is that if it's inside of square brackets, we're pulling it from a memory instead of pulling it from a register. So we use square brackets when referencing memory. Suppose that we see a register in square brackets. In that case, that will mean that the value in that register will be treated as a memory location, and the value in that memory location will be moved to the destination. This means that the example move EAX, comma, this piece, and the below example will have the same result. So move EBX, this piece right here, and move EAX, EBX, which is the contents of EBX, right? So moving into EBX, this element is going to then put this element inside of EBX. And then if I move EBX to EAX, then I have moved those contents inside of EAX, which will be exactly the same thing as this piece right here, because we're taking these contents and just moving them directly into EAX, which is what we see right here. So we can use the move instruction to perform arithmetic calculations when referencing memory addresses. For example, the below instruction calculates EP or EBP plus 4, adding an offset of 4 bytes to the memory location, and moves the value in the resulting memory address. So move into this location this specific value, which is inside of a memory location. The LEA instruction. So this is everything that we just talked about was a general instruction that is called the move instruction, and now we have the LEA instruction, which is another general instruction, and it stands for load effective address. So load the effective address, and this will be like LEA to this destination, whatever the source is. While the move instruction moves the data to the destination, the LEA instruction moves the address of the source into the destination. So the EBP value will be increased by 4 and then moved to EAX. However, if we had just used a move instruction here, we would have just moved the value itself, the data inside of it, to that location, right? So in this particular case, we're taking the address of it and putting it into EAX. We can notice that we have performed an arithmetic operation on a register and saved the result on another register using a single instruction. And what this arithmetic operation is that they're talking about is that they're adding the 4 bits at the end of it. The LEA instruction is often used by compilers, not for referencing memory, but so that an arithmetic operation is performed on a register and then saved to another using a single instruction. So you're not necessarily doing something to move locations, right? You're not using it for referencing memory locations, but so that you can actually have an arithmetic operation on the register and then save that to another location. Especially if an arithmetic operation are more complex, like adding and multiplying in a single instruction. And then we'll see that in a little bit. The NOP instruction stands for no operation, and this exchanges the value in EAX with itself, resulting in no meaningful operation. Hence, the execution moves to the next instruction without changing anything. These are used for consuming CPU cycles while waiting for an operation or other such purposes. It has no it has the particular syntax right here. You just say NOP literally. It's used by malware when redirecting execution to their shellcode. The exact location where the execution will redirect is often unknown, so the malware author uses a bunch of NOP instructions to ensure that the shellcode execution does not start from the middle. The padding of NOP instructions is called an NOP sled, and so if you can see a bunch of NOP instructions, you can assume that what's going to come next are going to be a set of instructions that will call the malware to do something. For example, redirect something to their actual shell code. Shift instructions are used to shift each register bit to the adjacent bit. So there are 2 shift instructions for shifting either to the right or the left, and it could be shift or SHR, right? Destination and count. So shift to this destination by the following count, and SHR is to the right, and then SHL would be to the left. So shift to this destination by this count, certain number of bits, right? So the SHR is shift right and the SHL is shift left. The instruction shifts the bits to the destination operand. The count decides the number of bits to be shifted. The bits which are shifted out to the location are filled with 0. So if we have this in EAX and shift it left, it will become this whole piece right here, and we're shifting it left 1 count, right? So you can see that it just moves, and then the new placeholder right after this 0 to the right of it is just this extra 0 that we saw. So we moved it left, right? The carry flag is used, and we talked about this in the last video, is used to augment the destination and is filled by the last bit overflowing the destination. So for example, if we have this ending in 101 and shifted right by 1, it'll result in this piece in EAX, and the carry flag will be set, meaning it'll have a value of 1. So again, remember, if you haven't seen the previous video, this is directly related to what we just talked about in this paragraph. The carry flag having a value of 1 or a value of 0, because we're talking in binary. And so if this is being shifted to the right, the carry flag will be set, and then it will have a value of 1, because that extra 1 at the end seems to have fallen off, but it's actually being stored inside of the carry flag. Shift instructions are used instead of multiplication and division by 2 or more powers of 2. So 2 to the power of n, essentially, where n is the count in the shift instruction. This saves execution time by not having to manipulate values in registers before performing multiplication or division. For example, if we have this that ends in 10 and we shift it to the right by 1 bit, we get this that has the 1 at the very end, which is the same result as dividing EAX by 2. Similarly, if EAX has 1 at the very end and we shift it left by 1, the result will end up being this, which is the same as multiplying it by 2. If that went over your head, I completely understand. Re-listen to it multiple times, because no matter how I paraphrase that or I try to change the phrasing of that, it's not going to make any more sense. So that specific piece, feel free to pause the video and try to kind of wrap your head around it. Again, it's not that big of a deal, because all of this stuff that we're talking about is going to come together at the very end of this, but it's just a building block. So we have rotation instructions. So the rotate instructions, they're similar to the shift instructions, and the only difference is that the bits are rotated back to the other end of the register instead of moving the overflowing bit into the carry flag or adding zeros instead of shifted out bits. The rotate instructions would be ROR to the right or ROL to the left, and the destination, and by a number of counts. So ROR instruction rotates it to the right, ROL rotates to the left. The rest of the syntax remains the same. As an example, if we have this 10 10 10 10 in AL, we can rotate it right by 1 bit and it will result in 0 1 0 1 0 1 0 1, like that. Similarly, rotating the result to the left will result in 10 10 10 10. So if you take this to the left again, it'll just result in 10 10 10 10, right? So rotate is it's kind of I would say I want to say that it does the same thing essentially that you would do with the shift left or the right. They're similar to shift left or the right. Is that it's just that the bits are rotated back to the other end of it instead of actually being moved to a carry flag, right? So this is essentially just taking this last 0 and putting it here. It's being rotated. So it's taking that last 0 and putting it to the front. And if we rotate to the left, it'll take this 0 and put it back at the end again, instead of putting it inside of a flag, for example. In move EAX EBX, which register is the destination? So remember, we're moving this to this destination. So in this particular case, EAX would be the destination. Which instruction performs no action, and that is the NOP, the no operation. All right, let's talk about flags. We did talk about flags in the last video, and the flags indicate the outcome of certain operations or conditions. They are bits in a special register known as the flags register or eFlags register. Each flag represents a specific condition or result of the most recent arithmetic or logical operation, and this is our table. So we talked about a few of these. We did not talk about parity. I don't remember talking about parity or auxiliary. We did talk about the 0 flag, the sign flag, the overflow. I don't remember if we talked about a direction flag, interrupt enable. We talked about a few of them. We haven't talked about all of them. So the carry flag is set when carry out or borrow is required from the most significant bit. We already saw this. Also used for bitwise shifting operations. Parity is set if the least significant byte of the result contains an even number of 1 bits. Auxiliary, the AF, is set if carry out or borrow is required from bit 3 to bit 4 in an arithmetic operation. It's called BCD arithmetic. Again, a lot of details here. You are not required to memorize this. I don't want you to feel like you need to know exactly what all of these things are. If you can memorize them, that's amazing. But for most people, especially if you have no background in any of this stuff, this is not going to be a really easy thing to wrap your head around. So ZF, 0 flag, is set if the result is 0. Sign is if the result of the operation is negative. The most significant bit is 1. Obviously, you can't have a -0, so you could have a -1. Overflow is set if the assigned arithmetic overflow, adding two positive numbers and getting a negative result or vice versa. Direction determines the direction for the string. So if df is 0, the string is processed forward. If df is 1, the string is processed backwards. And interrupt, if it's set, meaning if it has a value of 1, it enables maskable hardware interrupts. If it's cleared or value of 0, interrupts are disabled. They can be used in conditional jumps and are crucial for implementing conditional branching in assembly code. For example, you might only jump to a specific address if a certain flag is set or cleared. Which flag will be set if the result of the operation is 0, and that's going to be the ZF, the 0 flag. Which flag will be set if the result of the operation is negative, and that's a sign. So think about the sign flag as the negative sign, the minus sign, and that would be the SF. So now we can move on to arithmetic and logical instructions. So far, pretty much everything that we've talked about has kind of fallen under general instructions. Arithmetic operations, and I guess technically flags can also fall under arithmetic operations, but arithmetic operations are performed using arithmetic instructions. So if you know what arithmetic means, you can kind of wrap your head around what this would be. This might be a little bit easier to understand. So addition and subtraction instructions. So the syntax for this is as follows. You can add to this destination this value. You can subtract from this destination this value. That's basically it. And then the result will be stored inside of the destination or taken from that destination, right? So the value is subtracted from the destination. The value is added to the destination. The value can be either a fixed value or constant, fixed value constant or a register in its entirety. For the subtraction operation, 0 flag ZF is set if the result of the subtraction is 0. If the destination is smaller than the subtracted value, then the carry flag is set. Multiplication and division instructions, they use the EAX and EDX registers. Therefore, we will have to look at the last instruction that manipulated the register for every multiply and divide operation. To multiply, the following format would be used here. It multiplies the value with EAX and stores the result in EDX :EAX as a 64-bit value. Two registers are required here because the result of multiplying two 32-bit values can often be higher than 32 bits. And the lower the 32-bit values are stored in the EX register, the lower of those two values, are stored in the EX register, and the higher 32 bits are stored in the EDX register. The MUL value is essentially the syntax for multiplying, and then div value would be the syntax for dividing, and the value can be another register or a constrand as an immediate operand or operand. For the division instruction, the case is the opposite. It divides the 64-bit value in EDX EAX and saves the result in EAX and the remainder in EDX. So remember this one right here, these two are exactly the same, the format that you see right here, right? So the format for this element, that's not even something that you're going to end up doing. It's just that you need to understand what it actually is doing and which registers are being addressed for which one. And again, you can kind of refer to the last video just so you can see what all of the different registers were as we listed them, because there were a good amount of registers that we covered. Then we have increment and decrement or decrement instructions. And as the name suggests, the increment and decrement instructions increment or decrement the operand by a register of 1. And the syntax to increment EAX by 1 would be inc the EAX, and then similarly the syntax to decrement would be dec EAX. You can kind of also think about it as increase or decrease, but you shouldn't, just for full understanding, is to increment by 1 or decrement by 1. That's basically what this is going to be doing. We have logical instructions that are used to perform logical operations, and we have the AND instruction. So it performs a bitwise AND operation on the operands, and an AND operation returns an output of 1 when both the inputs are 1. Otherwise, it returns 0. So an example would be AND AL, which again, remember this is the destination, and then you have this value, and this is either coming from a register, and if it's inside of brackets, it would be coming from a memory location. In this example, 0x7c converts to 01111100 in binary. And this is just hex being converted into binary. There's nothing special about that. So suppose that AL had a value of 0xfc, which ends up being this in binary. In this case, the output of the above instruction will end up being 01111100. However, if it has the value of this, then it will be turned into this right here. So keep this in mind, right? So it's essentially doing this. It's looking at the two values, right? It's looking at, it says right here, right? If it will return an output of 1 when both of the inputs are 1, otherwise it returns 0, meaning if both of them are 1, it'll give you 1. If one of them is 0, it'll give you a 0, or if both of them are 0, it'll give you a 0. So this converts into this in binary. If it had this value, 0xfc, which is this, then the output would end up being this. So we're looking at 0, and then this one is 1, so that ends up being 0. Then this one is 1, and this one is 1, that'll give you 1, and then so on and so on. And then it gets to the last two digits, and the last two digits are also zeros, so it'll end up giving you a 0. However, if AL had a value of this, which ends up being this right here, then if we compare these two now, so if you have 1 and 0, then that'll end up being 0. If you have 0 and 1, that'll end up being 0. And then if you have 0 and 1, again, 0, 0. And so the only ones that end up coming back as 1 are the only two digits that actually have 1 right here, and then they also have 1 right here, and that'll end up being 1s, and then the rest of them will be 0s. So AND is essentially comparing the binary values of these two different data points, and then it's comparing to see if they both match as 1. If they do, it'll convert them into a 1. If either of them is 0, it'll be 0. If both of them are 0, it'll be 0. So that's basically it. The OR instruction performs a bitwise OR operation, and it returns a 1 if at least one of the operands is 1. It returns 0 if none of the operands is 1, meaning if you have two zeros, it'll return 0. If either one of them is 1, then you'll get a 1. So that's kind of the thing right here. You can pause this to look at these examples because I don't have to go back and forth for you to understand. But essentially, the AND one is saying both of them. So this needs to be a 1 and this needs to be a 1 in order for me to give you a 1. If both of them are not 1, then you'll get a 0. In this particular case, it's just saying if either of them is a 1, then I'll give you a 1. If both of them are 0, so if neither of them are a 1, then you get a 0, which is a little bit more inclusive. The NOT instruction takes one operand. It simply inverts the operand bits, replacing ones with zeros and vice versa. In the following example, if AL had this value, it would then turn into this value. So you don't want this, right? You don't want AL. You want the opposite of AL, which would just turn all of these into their exact opposites. The XOR instruction returns 1 if both the inputs are opposite. It returns 0 when both inputs are the same. This is performed by XOR instruction in assembly language, which performs a bitwise XOR operation on the operands, and it has the following syntax: XOR AL and then 0xfc, or 7c, excuse me. If AL has this value right here, the result of the instruction will end up being 1, 1, 0, 0, 0, 0, which is this. If it has a value of this, which is this piece right here, the result of the instruction will end up being this right here. If it has a value of this, the result will end up showing this. So it shows that XORing, we can call it a XOR, I guess, a register with itself results in 0. Therefore, the XOR instruction is often used to zero a register, which is more optimized than a move instruction. So it'll return 1 if both of the inputs are opposite. Okay, so if this, right, which the result of this will end up being this or this. Similarly, I'm kind of these digits right here are kind of messing me up, but this one actually ends up making more sense to me. So if it'll return 1 if both of them are opposite, meaning that if you have a 1 and a 0, which are opposites, then it'll return 1. If you have a 1 and a 1, which are not opposites, it'll return 0. If you have a 0 and a 0, it'll also return 0. So it's only going to return 1 if both of the inputs are opposite. That's basically how I understand it. In a subtraction operation, which flag is set if the destination is smaller than the subtracted value? And that is the carry flag. So let me see, my keyboard just times out. If I talk too much and if I don't use my keyboard, it'll just kind of go to sleep. Which instruction is used to increase the value of a register? Now, technically, it can be increment because it increases the value. But let's see if there's anything else. I want to say it's increase. Multiplication can also increase the value of it. Add can also increase the value of it. I think the answer that they're looking for would be add. Although technically multiply and increase both work. So let's see if it's add that they're not looking for add. So is it increase? Yeah, they're looking for increase or increment. So do the following instructions have the same result, yay or nay? So we have XOR EAX and EAX right here. Move EAX 0. They technically should have the same result, right? But it says, because remember, if it's going to return a 1 if both of them are opposite. So if they're both the same, it won't return a 1. It'll return a 0. And in this particular case, we're moving this 0 value into EAX. So technically, it should be yay. So let's see if I'm right. And I am right. Okay, great. Because it's comparing these two, right? XOR is comparing these two. And if they are opposite, then it will give you a 1. But if they're the same, it's going to return a 0. And then if you move into this destination the value of 0, then you're getting 0 in both of these. So yes, that is the same. So let's talk about conditionals and branching now. A lot of times the CPU has to determine if two values are equal to each other, if one is greater than the other, or if one is less than the other. And to perform these things, it uses conditional instructions. And we're going to be talking about those instructions in x86 assembly language specifically. The test instruction performs a bitwise AND operation. And instead of storing the result in the destination operand, as the AND usually does, it just sets the 0 flag if the result is 0. The instruction is often used to check if an operand has a null value, for example, by testing the operand against itself. This is done because it takes fewer bytes to use the test instruction than by comparing to 0. The test instruction would have this. So you want to test this destination against this source, right? So the instruction is often used to check if an operand has a null value by testing the operand against itself. And it's done because it takes fewer bytes to use the test instruction than by comparing it to the value of 0. So you're just testing these two against each other to see if they're equal to each other or if one is less than the other, etc. The CMP instruction, I would assume, is to compare, right? So based on the results, the CMP instruction compares the two operands and sets the 0 flag or the carry flag. It has the following syntax: CMP, destination against the source, and it works similarly to a subtract instruction. The only difference is that the operands are not modified. The 0 flag is set if both of them are equal, if the source operand is greater than the destination, so if this is greater than this, then the carry flag is set, and the ZF and the CF are cleared if the destination operand is greater than the source operand. So if they're both the same, right, it'll be setting the ZF flag. If this is greater than this, right, so if source is greater than destination, then carry flag is set. And if destination is greater than source, then both of the flags are cleared. So you would have 0 for this, and you would have 0 for the carry flag, which implies that this one is greater than the source. Branching. So when there's no branching, the instruction pointer goes from one instruction to the other in order that they are placed in memory. So it'll go from one place to another based on the order that they actually came in chronologically, we can say. The control flow remains in a straight line unless there is a branching operation. Branching operations change the value of the instruction pointer and change the program's control flow from linear to branching out. And again, instruction pointers were covered in the last video, so if you don't know what that means, you need to watch the last video. This is literally like a continuation from the last video. It's pretty much the same exact conversation. I mean, this whole thing is going to be about malware analysis, so technically it is the same exact conversation, but we are literally picking up where the last video left off. The jump instruction makes the control flow jump to a specified location, and it jumps to wherever the location is. The location operand will be moved to the instruction pointer, making it the address where the next instruction will be fetched for execution. And we have conditional jumps that have the if condition inside of it. If statements are used inside of coding a lot, and it says if something, then something. That's basically what it is. So in higher level languages, if they're said they help to fulfill the requirement. However, there are no if statements in the assembly language. This requirement is fulfilled using conditional jumps. Conditional jumps decide whether to jump based on the value of the flag register. Their syntax is similar to jump instruction, and the following table shows us what the condition, some examples that we have over here. So the instruction is JZ jump if the ZF flag is set, meaning if ZF is equals to 1, you jump. JNZ will jump if the ZF flag is not set, so the ZF would be equal to 0. JE will jump if it's equal, and it's often used after the comparison. JNE will jump if it's not equal, and it's often used after a comparison instruction as well. So then we have JG. If the destination is greater than the source, then you want to jump. It performs a signed comparison and is often used after a CMP comparison or instruction. JL would be jumping if the destination is lesser than the source and performs signed comparison, is often used after CMP. JGE is greater than or equal to, and it jumps if the destination is greater than, equal to, or the source, comparing to the above instructions. This LE would be lesser than or equal to. So if the operation is lesser than or equal to, if the destination is lesser than or equal to the source. JA, jump if above. So similar to JG, but performs an unassigned comparison. JB, jump if below. If you don't know what above or below means, that means you have not seen the last video. So there is an order of things that comes in when you're looking at the stack. And so either things are above or below each other. JAE, above or equal to. JBE, below or equal to. So which flag is set as a result of the test instruction being 0? And that would, of course, be the 0 flag. Which of the below operations uses subtraction to test the two values, 1 or 2. So you have compare or you have test, and if I remember correctly, test uses subtraction. Compare just compares the values to each other. Oh, I'm wrong. So compare uses subtraction to test. Yeah, I'm sorry. Yeah, my bad. That's my bad completely. I want to blame it on dyslexia, but I think it's because I fully didn't recall the data from those sets of instructions. Compare uses subtraction to test two values. Which flag is used to identify whether a jump will be taken or not after a jump 0 or jump not 0 instruction? And we have these values right here, but it is the jump flag, I want to say. So a conditional jump will end up being the thing. So would it be the jump flag? I think it is the jump flag. So something will jump if it is not. So let's see if it is the jump flag. It's not. So the 0 flag. Yeah, so it's the 0 flag. So if it is 0 or if it's not 0, that's the flag that's being used to identify whether a jump should take place. All right, so stack and function calls. Now going back to the concept of the stack based on what we talked about in the last video. In the last video, we talked about how important the stack is, and it ends up being the target for a lot of malware to operate in or to manipulate the data that's inside of the stack. We also learned about the registers that are used to reference the location of the stack, as well as the concept of the last in, first out memory, which means that the last variable that's pushed onto the stack is the first that will be popped out. And these push and pop operations are performed by following instructions in the assembly language. The push instruction is push source. So it'll push the source operand onto the stack. The value of the operand is stored at the memory location pointed to the stack pointer, the ESP, effectively becoming the new top of the stack. So when you add something to it, that's going to end up becoming the top of the stack. The stack pointer is then adjusted, which means it's decremented to reflect the updated top position of the stack. So the pointer is everything other than the stuff that's just being pushed on top of it, right? So everything, so let's say this is the top, all of this stuff ends up being the pointer, which means all of this is going to be decremented, decreased by 1, right? So it's going to be decremented, meaning it's going to move down one place so that we can add this thing to the top of it. That's what all of that actually means. The following instructions also push all of the general purpose registers to the stack. So push A, also known as push all words, it pushes all the 16-bit general purpose registers to the stack, for example, AX, BX, etc. Push AD pushes all of the double words, all the 32-bit general purpose registers to the stack. So EAX, EBX, etc. And if you don't know what that means, watch the last video. When we encounter these instructions, it's also often a sign of someone manually injecting assembly instructions to save the state of registers, and it's often the case with shellcode. The pop instruction is taking something off of the stack, right? So push puts something on the stack. Pop retrieves the value from the top of the stack and stores it in the destination operand. As a result, the stack pointer, ESP, is incremented to reflect the adjustment. So again, if you're taking this off, that means these things are now going to move up by 1. So it's going to be incremented. The following instructions also pop all the general purpose registers. So you have pop A, which will pop all words, which means all of the single, the single words, and you have pop AD, which will take all the double words, meaning all of these things right here. The call instruction is used in the assembly language for performing a function call operation to perform a specific task, and it has the call location. So depending on the calling convention, the arguments are placed on the stack or in the registers in a function call. The function prologue, if you remember this, we talked about this in this video. The function prologue prepares the stack by adjusting the EBP ESP and pushing the return address on the stack. Similarly, when it returns the epilogue, so this is the way that the function will exit, restores the stack for the caller function, and we'll learn more about these things in upcoming videos. So in the next task, we're actually going to practice using all these things. So which instruction is used for performing a function call? And that should be the call. Which instruction is used to push all registers to the stack? And that should be, or push all registers, it would be push A. There we go. All right, let's do some practice now. All right, so we're going to apply everything that we've learned so far in this video and the last one, and it's going to be on this view side. I'm going to zoom out and put it into full screen so that it's a little bit easier for us to handle. The options on the top bar could be run the program, execute the next instruction, stop the execution, restart the program. And we have instructions that we should be doing basically. So contains the following assembly code instructions. Run these instructions and observe how they impact register, flag, etc., etc. And the following instructions demonstrate how different arithmetic instructions work. The following instructions demonstrate how the data can be moved into registers, from register to register, from memory to register, etc. And the stack, so they demonstrate two instructions, push and pop, used to push data into a stack and pop the data out. And then CMP and test instructions, and we have these available for us as well. I mean, we already know essentially what these things are going to do. So we just need to run them. So while running move, what is the value of EAX after running the fourth instruction in hex, etc., etc. So that's pretty much it. That's all we got to do. So what I'm going to do is I'm going to zoom out and click the view site button so that we can actually access the site, so that we can run the commands. And let's see if I do need to go into, let's see, would you take a guided tour to look more about, yeah, why not? So we'll take a guided tour, kind of understand what's going on, and then we will make modifications and see what the results are. So let's see what the guided tour is. We have the control buttons. Run all the instructions at once, run instructions one by one, reset all memory. So run all at once, run by one, and then reset. The next one would be you can choose different sets of instructions, so arithmetic code or other general types of code. Instruction block would be the stuff that you want to do. You can see different instruction codes. The green arrow presents the running command. Then we have the registers and the flags. So you'll see the register value and checkered flags, which is what we have here. And then these are the flags that we can check. And at the bottom right here, the memory block. So with the current command memory. And then finally, we have the stack and pointers, which is right here. And I think that's pretty much all of it. So I think this should be fine to use in one window. It says that we can expand it into a new tab in a full window. And I guess this might be a little bit easier to navigate, and I can still zoom in and zoom out accordingly. So we'll just do it that way, I guess. So we'll do it like this, and then we'll try to find the answers to each one of these questions. I'll kind of zoom out of this, and then we'll be able to move into our questions. So here we go. First question says, while running the move instructions, what is the value of EAX after running the fourth instruction? And they want the hexadecimal value. So EAX under the move instructions that we have right here. So while running this, and now we can see right here. So what is the value after running the fourth instruction, which is this piece right here? What is the value of this in hexadecimal? So the first thing that we have to do is we need to change this to move instruction and come out here. And I think if we just click this, we end up seeing the values here. And so if we move down to the fourth instruction right here, so you can see move EAX 40, it says what's the value of it, which ends up being this guy right here in hexadecimal. So that should be the value. So let's go down here and see if that's indeed the case. And let's paste that and test that. Okay, cool. Yeah, that is the case. What error is displayed after running the sixth instruction from the move instruction section? So we are now on 4. Let's move to 5 and 6. And it says error, memory to memory data movement is not allowed. So that's the error. So let's go here and paste that here. Run the instructions from the stack section. What is the value of EAX after the 9th instruction in hexadecimal? So let's see if we have a stack. There we go. That's the stack section. And the 9th instruction is technically position 8 because it starts at 0, right? So what is that's what it's saying, right? Run it. I don't know what's the value of the EAX after 9 instructions. So we're just going to click this 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the value of EAX after the 9th instruction. And what we see here is as such. So let's copy that and take that. There you go. Run the instructions from the stack. What's the value of EDX after the 12th instruction? So we're technically on 9. That would be 10, 11, and 12. And the value of EDX is right there. So, I mean, I'm literally just copying these things by just clicking play one by one. I'm not doing anything crazy. So there is that. Run the instructions from the stack section. After pop ECX, what is the value left at the top of the stack? So pop ECX. We have pop ECX right here. What's that after the stack? So I'm going to reset this whole thing because I want to stop at pop ECX. So we're going to go 5, 6, 7, 8, 9, pop ECX. There we go. What's the value at the top of the stack, right? That's what it's asking in hexadecimal format. So this is the stack right here. And technically, from what I understand, the bottom is the top of the stack and the top would be the bottom of the stack. So I want to say it's this thing right here. So let's see if that's actually the answer. Hopefully that's right. Oh yeah, okay, great. Run the CMP and test instructions. Which flags are triggered after the third instruction? These abbreviations in alphabetical order with no spaces: CF, PF, SF, and ZF. So let's see, we're going to go to the CMP and test instructions, and it says use these abbreviations in alphabetical order with no spaces: CF, PF, SF, and ZF. Okay, so after the third instruction, let's go 1, 2, and 3. And it's saying which flags are triggered. Okay, so this is basically the flag. So parity and 0. So it would be PF for parity and then ZF for 0. Run the test and the CMP instructions. Which flags are triggered after the 11th instruction? So test and CMP, we're technically on number 3. So 4, 5, 6, 7, 8, 9, 10, and 11. It ends up giving us CF for carry and then SF for sign. So CF/SF. Run the instructions from the LEA section. What's the value of EAX after running the 9th instruction? So we'll go to LEA, which is the last one. And what do we have? The value of the 9th instruction. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the value of EAX is this right here. And last but not least, run the instructions from LEA. What is the final value found in ECX register? So 1, 2, 3. The final value should be that. That should be the answer. And that's it. That was very straightforward. I was kind of nervous because I didn't know exactly what we were going to end up doing. And to be brutally honest with you, I have to review all of these contents just to remember what all of these things are. Because the biggest confusion for me are not these initial instructions. It's what EAX was and EBX and all of these things, what ECX and what EDI and all of those things were, because we talked about those in the last video, and this is my very first time being exposed to all of this content, so it was not, I didn't memorize it. As I mentioned multiple times, it's like this is not going to be something that you're going to end up learning how to memorize immediately unless you just have amazing memory. So but yeah, that's pretty much it. Let's do kind of a little bit of a review and we'll do a wrap up. So basically what we looked at was what the common assembly language instructions are in the x86 architecture, and obviously there's a lot of other stuff because this is not the be all and end all of this conversation. This specific topic for x86 architecture can go very, very deep, as I'm sure you can imagine, because this is, again, not something super easy to wrap your head around. We covered the ones that operations are performed in assembly languages, and as we move forward to the rest of the videos in this module, we're going to learn about some of the more instructions as per requirements. And so far, we've covered opcodes and how we can convert them into assembly language, general instructions such as move, load effective address, and shift and rotate, arithmetic instructions like addition, subtraction, multiplication, division, and conditionals, and how we can use them for branching, stack, and with the push and pop to make sure to adjust the positions inside of the stack, and function calls. You can reach out to TryHackMe inside of their Discord channel, or you can hit them up on X, formerly known as Twitter. And that is pretty much it, my dear friends. I know, again, for me, this was not something that I can understand by just going through it once. So if you are a genius when it comes down to this kind of stuff, I'm kind of jealous. But at the same time, you should have an easier time going through this information. If not, review it. If you really want to go into malware analysis as a role, you should understand these things. And I personally don't. So I'm not that excited about this kind of information, but at the very least we have a recording of it, and I can use it in the future to remind myself of this data point. And honestly, I feel like I'm going to re-review the contents just because I want to have a little bit of a better understanding. I don't want to feel as unknowledgeable. I don't know if that's a word, but I don't want to feel this badly about this kind of information, because it really, like, it was my first exposure to this, so I'm rambling at this point. But yeah, feel free to review and of course drop any questions if you have any questions, and I'll do my very best to answer them for you. All right, and that is it, my dear friends. If you got value out of this room and out of this video, and if you would like to get more videos like this one, I do encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel, especially on SOC level 2, as we wrap up the pathway and as we get into pen testing more, and as we get into AI for cybersecurity as well. Drop any questions or comments that you have in the comment section below and let me know, and I will do my very best to respond to them. But apart from that, make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel. If you're serious about your CySec training and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comment section. And that's it for today. It's your boy Hank Hackerson at Hank Hacks Hackers. If you're ever a network and system attacker/protector, if no one else loves you, Hank loves you. Love, peace, and chicken grease, and I'll see you in the next video later.